Good afternoon. I will be posting a series of videos for Chapter 10, and most of these videos will just have several problem solutions in them. I think at this point, at least for this chapter, I'll be prioritizing the solution of problems over lecture presentation. This chapter is continuous with Chapter 9. A lot of books would combine these two chapters into one big chapter because work and kinetic energy go hand in hand with potential energy. So first we need to talk about potential energy. I'll use this problem as an excuse to introduce the concept. We're told that a person, they're inside a gymnasium and they throw a ball up into the air. The ball has a mass of 100 grams, and we're supposed to figure out just how fast they have to throw that ball so that it makes it all the way up to the ceiling of the gymnasium, which is 10 meters high. Now, we could do this with kinematics. You could have done this problem months ago using constant acceleration kinematics, but now we can do it more simply using the principle of energy conservation. So the first thing we have to talk about is the relationship between the work done by gravity and this change in so-called potential energy. So can we agree that as the ball rises through the gravitational field, when the ball is right here, its velocity is tangent to that parabola, and gravity pulls straight down. And we can agree that since the angle between those two vectors is greater than 90, it's between 90 and 180, when we go to calculate the work, we would find that the work done by gravity is negative. Gravity is doing negative work on the ball as it rises. And that means that it will be decreasing the ball's kinetic energy. So the question is, where is that energy going? The ball has kinetic energy, but the kinetic energy is going away due to the work done by gravity. So where does that energy go? If we were talking about sliding, kicking a box across a garage floor, when you kick the box, it immediately starts to slow down, and then it comes to a stop. And I think we know that the energy it had, the kinetic energy that you gave it, gets dissipated as thermal energy, right? That's the heat, if you want to call it that, that's dissipated in the surface of the box and the floor. But in this case, there's no mention that's been made of air drag or friction. So where does the energy go? It's not dissipated as heat, because you could do this on the moon where there is no atmosphere and no air, and you'd still find that the ball would slow down. So where does it go? Well, some of you have taken other physical science classes, and you're familiar with this concept of potential energy. We know that the ball on the way up slows down. It'll come to a stop just for a moment at the apex, but then it's going to speed right up again. So it's like it gets that kinetic energy back. It has the kinetic energy, and then that energy is transformed into some other form that's not as obvious. We don't see it because the ball is not moving as quickly. We don't see the energy the way we did before, but then the energy comes right back. So you could think of it as being stored in some other form, and then that energy comes right back as kinetic energy. And that other form is what we call potential energy. So just to make this really clear, suppose that when you threw this ball, you gave it 10 joules of kinetic energy, 10 joules. When it gets to the top, just for a moment, I drew an actual parabola here, but suppose the ball just goes straight up and then straight back down. If it goes straight up, then when it gets to the top for a moment, its speed is 0, and that means that its kinetic energy would be 0. So if you gave it 10 joules of kinetic energy, and then for a moment, it had no kinetic energy, well, where did all those 10 joules go? They're all in the form of potential energy. On the other hand, couldn't we just use the work kinetic energy relation and say, if the kinetic energy just decreased by 10 joules, that's a delta K of negative 10, that must be the work done by gravity. So gravity did negative 10 joules of kinetic energy. So let me summarize those two statements. If you gave the ball 10 joules of energy when you threw it, and when it gets to the top, it has 0 joules of kinetic energy, that means 10 joules of kinetic energy were just transformed into potential energy. And we use the letter U. So the change, I'm gonna write this on a different place here. The change in gravitational energy was plus 10. That's an increase of potential energy, but the work done by gravity would have to be negative 10 because the work done is equal to delta of kinetic energy. And we know that kinetic energy decreased by 10. So work done by gravity and the change in potential energy associated with the gravitational force, they have the same magnitude. They're both 10, but they're opposite in sign. And it's such a basic relationship, but it's fundamental to this chapter. The change in potential is the negative of the work done. And I'm going to emphasize that this is true for so-called conservative forces. I'll talk more some other time about conservative forces, but you should know that gravity is the most common example in this class of a conservative force. The work done by a conservative force is the opposite of the change in the potential energy. Let's consider the second phase of the motion here. When this ball falls back down, it's falling down and gravity pulls down. So gravity would be doing positive work. We can also see that from this relation. Positive work is associated with a positive change in kinetic energy. But wouldn't the ball be losing potential energy? We know that the higher it is, the more potential energy it has. So as it's falling, it's losing potential energy. That means delta U would be a negative number. Delta U is a negative number in this case, but the work done by gravity is positive. Again, they have the opposite sign. Okay. Remember where this comes from. This is from F equals ma. Now, everything I just said about potential energy, I didn't prove it necessarily. I didn't use any math to motivate that, but you know where this comes from. We started with F equals ma and we integrated it. So this is as true as F equals ma. Let's now incorporate potential energy into this equation. And I can do that this way. I can break this work up into two parts. There's work done by gravity, and then there's work done by all other forces. That's one way I can break this up. I'm sorry, this should say delta K. All right, well, I made the assertion that the work done by gravity is the negative of the change in potential energy. All right, and now we're getting somewhere here. This equation looks different from this one, quite a bit different, even though it came from that equation. Let's take the delta U and put it on the other side. And this is not an equation presented in your book. They actually take it a step or two further, which we will do as well. But this is a perfectly valid equation. It's useful if you're solving a problem where the only conservative force is gravity. Now, there's really not that many conservative forces that you have to keep track of in this class. I'm going to give them to you right now. Basically, it's gravity and springs. That's it. A spring that obeys Hooke's law has an associated potential energy, which we'll get to, and then there's gravity. That's it. But if your problem only involves gravity and not springs, you are welcome to use this equation. And I'm going to use this equation for problem 10.5 right now. I think it probably is worth memorizing this. Well, it's really more important to know how to get from here to here, just to substitute the change in, or the negative change in gravitational energy for work done by gravity. Okay, let's solve part A of this problem now. They're asking, how fast does this person need to throw the ball to get it up to 10 meters if the ball is thrown from a height of 1.5 meters? Okay, the first thing we should do is pick a coordinate system. I'm going to put the y coordinate equal to 0 down here. So my coordinate system is this one, x, y, but the origin, don't be confused. When I drew my axes, I put an origin here, but I really mean the origin to be here. This is just showing which direction the axes point in. Okay, so this is the ground, y equals 0, and y is increasing in that direction. Now, delta U gravitational is the negative of the work done by gravity. The gravitational force in this chapter we regard as a constant. And remember, instead of doing the integral of f dot dr, if your force is a constant, you can use this very simple formula. You just dot the force with the displacement. So if your gravitational force is constant, this would always be valid. This is the work done by gravity. Of course, I need the negative sign to get the change in potential energy, because I'm using this relation, which you must memorize. You must memorize this. Okay. Remember, the gravitational force, if I write it in vertical column notation, it's 0, negative mg. The force points down, and I'm calling up positive. And then delta r, well, that's just, you've got an x component called delta x and a y component. When you dot these two, I'm going to use the Cartesian method. I just multiply the x components together, I get 0, and then I multiply the y components together and add. So this just ends up being negative mg delta y, and you can see that the negative signs cancel, and we get this simple expression, mg delta y. All right. That's probably worth memorizing as well. In this chapter, usually it's acceptable to use this formula for the change in potential energy. It depends on how heavy the thing is and the distance through which you lifted it. Of course, it also depends on the strength of the gravitational field. Now, one word of caution, this is only true if you call up the positive direction. If I had called down positive, I think we would pick up a minus sign here. So I would not even mess with that. If you're going to deal with gravitational energy, just play it safe and call up positive. Okay, now this problem is very simple, and yet I've already spent, 10 minutes setting it up. That's because I haven't had any lecture presentation about this. But once you're familiar with the use of potential energy, some of these problems will go real quick. Okay, let's define some times here. T0 is when the ball is released. T1 is when the ball reaches the top of its trajectory. I'll just say ball reaches apex. And T2 is when the ball strikes the floor, because we know it's going to come back down. And right now we're looking at what happens between times T0 and T1. That's on the way up. Okay. So I'm going to apply this equation between those two times. The work done by forces other than gravity will be change in kinetic energy plus change in gravitational energy. But there's no mention of air drag, so we don't have to worry about the work done by drag. There's no friction. Nothing else is touching the ball. The only force doing any work would be gravity. So this is just 0. That's kind of interesting. The change in kinetic energy plus the change in gravitational energy has to be equal to 0. Or what you could say is delta K is the negative of delta U gravitational. And that's a very interesting statement. It says if your potential energy increases, then your kinetic energy must decrease. Makes perfect sense, right? When you throw something up, it's gaining potential energy at the expense of kinetic energy. It's losing kinetic energy and simultaneously gaining gravitational energy. That's what this equation says. Okay, well, since I've picked my subscripts for the various times, delta K between times T0 and T1 would be 1/2 m. I'm factoring out the 1/2 m, so I've got V at the top squared minus V when it's thrown squared equals negative, and we've already decided this is our expression for the change in potential energy, so negative mg delta y. And now we're actually starting the equation here. By the way, you may have solved this differently if you've already been reading. I hope you've already been reading. There's more than one way to use the potential energy to set up your equation, and I'm going to try them all out as I work through these solutions. At the top, remember, if you threw the ball straight up, then it stops for a moment when it gets to the top. So that quantity is 0. And it looks like we've got the minus signs canceling here. Okay, and I can just write this, 1/2 mv0 squared equals mg times y at the top minus y at the bottom. And this has a very simple interpretation. You probably could have jumped straight to this equation if you were more familiar with using potential energy. What does this say? This is the gain in potential energy as the ball goes from 1.5 meters to 10 meters at the ceiling. This is how much extra potential energy it has. Where's that supposed to come from? It comes from the kinetic energy that the person gave it. So the kinetic energy that the person gave to the ball by doing work on it when they threw it, all of that kinetic energy is transformed into additional potential energy. And now we can just solve for the speed. And we get root 2g. Notice how the ends cancel. That's interesting. Doesn't matter how massive the ball is. We get this very familiar equation. I feel bad that this is sticking way out here. I can't use it. I guess I could put extra parentheses there. All right. It's just looking weird to me. Root 2gh, basically. We've seen this before. So that's encouraging. Let me plug in numbers now. 2 times 9.8. Well, let's see. We ended at, 10 meters at the ceiling minus the 1.5 where we started. So 8.5 meters. Oh, there we go. 8.5 times 9.8 times 2. This thing would have to be thrown at 12.9 meters per second. You probably could have done this without energy. You could have done it with the kinematics, but very often it's easier this way. I'm checking the solutions to make sure they have the same number. Yes, they round to 13 meters per second. And part B, now they want to know, okay, how fast is this ball going when it strikes the floor? And as usual, we will ignore air drag. Let's not even worry about that. There's a couple ways we could do this. We could look at the change in kinetic energy and potential energy from the top to the bottom, or we could go from the starting point to the ending point and skip whatever happens in the middle. It works both ways. Let's do my first suggestion first. Let's look at the energy here and the energy here. And I will be using this same equation. So I'll say from T1 to T2, the work done by other forces other than gravity specifically, would be the change in kinetic energy plus the change in gravitational energy. Just like before, there are no other forces. Gravity is the only force doing work. And that means the change in kinetic energy is the negative of the change in gravitational energy. Okay, well, now the 2 times T1 and T2 mean I should write 1/2 m V2 squared minus V1 squared. This is final kinetic energy minus initial kinetic energy. And that's going to be negative mg y2 minus y1. Same setup as before, but now the numbers are different. Okay, we're looking for V2. I should have pointed that out. I think I did say that. How fast is the ball going when it strikes the floor? That would be the speed at time 2. That's what we're looking for. But remember, the speed at the top, V1, is 0 by assumption. The m's cancel just like before. So it looks to me like V is equal to, now let's check something here. We're going to be taking the square root. That means we better be taking the square root of a positive number. Y2 minus Y1, isn't that a negative quantity? Isn't the displacement from here to here negative? So this is in fact a negative number. A negative makes positive. We are taking the square root of a positive number. So root 2g, and then I could use the minus sign to flip the signs there, y1 minus y2. And that's the square root of 2 times 9.8 times, well, y1 was 10 meters, and y2 is 0 because it's on the floor. That's where I put my origin. 2 times 9.8 times 10. And now we're going 14 meters per second. A little bit faster than they threw it. So we found that they only had to throw it upwards at 12.9 to get it to the top. But then on the way back down, it's going to fall a little further. It makes sense that it will be going faster. Okay. So what can we take away from this problem? By the way, I'll point out we have another similar looking expression. It looks like root 2gh, does it not? Okay. I solved this problem really by using F equals ma in disguise. I started with work equals delta K because that's the integrated form of F equals ma. But then I chose to break the work up into parts, work done by gravity, work done by non-gravity forces. That was 0 for this problem. And then instead of talking about the work done by gravity, I instead talked about a changed potential energy. So the fundamental relation here was this one. Change potential is the negative of the work done. And I went ahead and calculated that. Work done by gravity, in this chapter, that's very simple because we regard the gravitational force as constant. And this is the work done by gravity right here. It's negative mg delta y, but change in potential is the negative of that. So this was the functional equation. The operative, what's the word I'm looking for? That's the one we really needed to finish the problem. Okay, at this point you might be thinking, I could have done this with kinematics. Do I really need this? It does make some problems simpler. You'll see that as we go through more of these problems from the chapter. Next up is number 13 from the same chapter. This problem should give you some sense of the huge advantage of solving things using energy considerations rather than talking about forces. Keep in mind that when you apply F equals ma, that's a vector equation. You have to deal with vectors. You have to break vectors into their components, apply the equation along 2 or 3 simultaneous axes, or 2 or 3 axes simultaneously. You have to worry about minus signs. You have to take components. Using energy is often simpler because energy is simply a scalar. It's just a number. It's not a length and a direction the way a vector is. And you'll see that in this problem. So we're told that there's a cannon. I paused and took about an hour to come up with this masterpiece here. And I had a bunch of rough drafts that just didn't cut it, so I threw them out. But finally, I got a painting here that's up to snuff. We're told that the cannon is launched at 30 degrees above the horizontal, and it comes out really fast. This is, what, 200 miles per hour? And the cannon is launched from on top of a hill that's 10 meters high. That's, what, 33 feet? So if it's launched at 80 meters per second, how fast is it going when it hits the ground? Now, in real life, at that speed, this cannon would experience significant air drag, lots of air drag, and a whole lot of the energy would be sapped from the ball because of that dissipative force that we call air drag. And so the answer that we get is really much too high. However, it's not that difficult to account for air drag if you have a computer to assist you. And we were going to do that in lab this semester, but boo-hoo. Kind of missed out on that opportunity. In any case, let's solve this using the same relation as before. The change in gravitational energy is the negative of the work done by gravity, but the work done by gravity is negative mg delta y. Remember, you can only use this if your gravitational force is constant. When we get to chapter 13, we're going to account for the fact that gravity does get weaker as you rise above the surface of the Earth. But for most of the problems we do in these chapters, or at least this chapter, we're not talking about heights like the International Space Station. We're barely even talking about the height of a mountain. So this 9.8 doesn't change by enough to justify using the full integral expression for work. We can just do Fg dotted with delta R. Okay, just like the previous problem, I'll say work done by non-gravitational forces would be the change in kinetic energy plus the change in gravitational energy. And if there is no air drag, that's gone. And we just say delta K is the negative of delta U. The problem is asking, I forgot to state, the problem is asking us how fast, no, I did state that. How fast is the cannonball going when it strikes the ground? So T0 is the launch time, T1 impact. And let's do this. The change in kinetic energy would be 1/2 m v final squared minus 1/2 m v initial squared. So I guess this time I'm choosing not to factor out the 1/2 m. And that's got to equal, okay, don't forget, the work done is negative mg delta y, but the change in gravity energy is the negative of that. So it's actually positive mg delta y. So check it out. If the cannonball was rising between 2 times, then the potential energy would be increasing because delta y would be, let me emphasize, I'm using this type of coordinate system. If delta y is positive, then I said that backwards. Let's see. Look at the right side here. This is negative delta U. If delta Y was positive, yeah, I left out the minus sign. Wait a minute. Am I goofing this up? I've got so many minus signs running around. I think I'm second guessing myself. Let's just check here. If the ball was rising, delta Y would be positive, and that means that your final velocity would be greater. See, that doesn't make sense, does it? Okay, I have to pause and figure out where I goofed up. Okay, I didn't goof up. I just got confused with all the minus signs. Work done by gravity is in fact negative mg delta y, which means delta g is positive mg delta y, but delta k is the negative of that. So that's what goes in here. I could have just recognized that, isn't this the work done by gravity, which is negative mg delta y? Okay. Honestly, in a moment, I'm going to present an alternative starting point for these problems that's really easier to think about. So I think we'll just solve this problem that second way as well. In this case, neither of the velocities is 0. I can't cross any of them out, but I can divide by m. You see that? So let's divide the equation by m. Let's multiply the whole equation by 2. And that shows me that the speed squared at the bottom would be 2. Let's see here. That's v naught squared minus 2g delta y, right? I believe I did that correctly. And then we want the square root of that. Okay, so it looks kind of like root 2gy, but it's a little more complicated because of that other velocity. So let me plug in numbers. 80 meters per second squared minus 2 times 9.8 times 9. Here's where you have to be very careful. This is the change in y. It's the displacement. We started at 10 meters and ended up at 0. So the displacement is actually negative 10. In fact, I'm going to write that all out so you don't get confused. 80 meters per second squared minus 2 times 9.8 times the displacement of negative 10. So we're actually adding a quantity here. And when I take the square root, I get 81.2. Okay, that's not a whole lot faster, but it did speed up a little bit. So make sure you're careful with your signs. Now, what if we had to solve this problem with kinematics? Would it have taken more or less time? I suspect more time, because in kinematics, you have to apply F equals ma along the x and y axes separately. So what you'd have to do is first resolve this velocity vector into components. You'd have to find v naught x and v naught y. Those are the initial velocity components in x and y. Then you would have to apply kinematics separately. F equals ma is not really necessary because remember, we started this class talking about projectile motion before introducing F equals ma. We just assumed that the acceleration was 9.8 straight down. But still, you'd have to apply your kinematic equations along 2 axes in order to get the final component. So your final velocity vector looks like that, and it's got x component and y component. You'd have to find the x component of v1, the vector, and the y component, and then say this, v1 is the square root of v1 x squared plus v1 y squared. That's more work. So I think that this method is definitely simpler. And if I didn't have to go through all the background stuff, it would be simpler still. So let's make this even easier now. And look more carefully at this relation. Delta UG is equal to the negative of the work done by gravity. Oftentimes, instead of talking about the change in potential energy, it's easier to just talk about the potential energy. Like, wouldn't it be nice to just assign an absolute value or a particular value to the potential energy for a mass at any height? Like if you know what the mass is and you know how high it is, boom, you know the number. That would be even nicer. So we're going to do that with this equation. Compare U at arbitrary height to U at the ground, or really just some origin. I'll even say at some reference height. Okay. Well, remember, didn't I already come up with this? We looked at the work done, we took the negative of that, and UG, delta UG is mg delta y. So here's y equals 0. Maybe this is the floor of your classroom. Maybe it's the ground outside. And here's some arbitrary height, which I'll call, how about y final? So y initial is 0 and y final is just some number. Okay, let's take this equation and put in subscripts. So the change in energy between these two places, let's say we go from here to here. That's why I'm calling it initial and final. That means UG final minus UG initial equals mg and then times delta y. That would be y final minus y initial. But because of my choice of origin, I've decided to say that the initial y coordinate is 0. This is the origin for the y-axis, at least. The y-axis goes like this, and this has a y coordinate of 0. So the gravitational energy at the final position would be the gravitational energy at the initial position plus, and I'm going to go ahead and cross this out now because I put the origin there, plus this term, mg y final. And we're very close now to the most essential equation regarding gravitational energy. I shouldn't say the most essential, but perhaps the most practical. Yeah, the most practical as far as solving problems. Here's what it says. If you want to know what the potential energy is up here, all you have to do is take whatever it is down here, that's what I'm calling UG initial, however much potential energy something has down here, just take that number and add mgy, where y is the additional height above your reference height. That's it. So mg, that's force, times your height over and above the reference height, that's the extra potential energy that you have over and above whatever you had at the reference height, or on the ground, on the floor, whatever. That's the essential physics there. Hopefully you can take that away. The potential energy up here is the same as the potential energy down here plus mg times this distance. That's it. So let's just dispense with the F for final. And how about we just say the potential energy at any height y is the potential energy, I'll put sub-0, meaning at the ground, plus mg y. Take the potential energy on the floor, add this amount, and that'll give you the potential energy at height y. Now, what is the potential energy on the floor? That's a little puzzling because if you're in the classroom and you set a brick on the floor, you might say, well, it's got 0 potential energy, it's on the floor. But for somebody outside standing on the ground floor, I'm imagining that we're in the 3rd floor of the D building. Somebody outside on the ground would say, oh no, it's already like 10 to 15 meters up in the air. It definitely has potential energy. If you were to take that brick and carry it out the door and drop it off the balcony, it's very clear that it had potential energy because it's moving. That potential energy has been transformed into kinetic energy. So it really depends where your ground is. I mean, even outside on the ground, if you could somehow excavate a huge amount of earth from beneath the brick, now it's going to fall even further. So it's really up to you. It's arbitrary. This potential energy is completely arbitrary. It doesn't affect the physics. The meaningful equation is this one. This is the physically meaningful equation. It's all about change in potential energy. But when it comes to using this equation, you can pick whatever value you want. And I know I'm making this a little bit long-winded, but it's because I want you to understand where this equation came from. Let's pick the most convenient possible value. What would be the easiest number to assign to the potential energy of anything when it's just sitting on the floor? I think that would just be 0. So let the gravitational energy at height y equals 0 be 0. And then the potential energy is really simple. It's mg y. Memorize that. That should not be on your note card. If you write that on your note card, it means you didn't study enough. It means you're totally unprepared. This should just be memorized. mgy is the potential energy of an object of mass m in a gravitational field g at a height y above your reference potential, where by assumption, the potential energy would be 0. So this equation only works if up is positive and if u equals 0 at the reference height. These two have to be true if you're going to use this formula. If you're not making these assumptions, then it's a little, you might have to go all the way back to this starting point. So those are some subtleties there that most books tend to gloss over. You know, they just kind of set this up once and then run with it. But as long as you set up your coordinate system this way, you can always use this, at least in this chapter. Like I said, in future chapters, we're going to account for the fact that G is really not 9.8. Even at the top of Mount Everest, it's a little less than 9.8. By the time you get out to the moon, it's way less than 9.8. So this would be completely bogus if you were using it for like satellites way out in space. Okay, let's go back and do this problem with this formula now. Before, my starting point was this, was work done by forces other than gravity is equal to change in kinetic energy plus change in gravitational potential energy. Now, if there is no work done by other forces, then the left side is just 0, and you would find that the change in kinetic energy is equal to the negative of the change in gravitational energy. Well, instead of times 1 and 2 or 0 and 1, let's just go with initial and final. K final minus K initial equals, well, without the minus sign, that would be UG final minus UG initial. The minus sign is going to flip the order. So this would be UG initial minus UG final. And now let's do this. Let's put everything with an F on one side of the equation and everything with an I on the other. So final stuff on one side and initial stuff on the other side. And this is awesome because conceptually it makes so much sense. It says before the cannon, well, right after the cannonball was launched, it had a certain amount of kinetic energy because it was moving, and it had a certain amount of potential energy because it was launched from above the ground. And when you add those two up, you get some fixed quantity that we'll just call the total energy, and that has to equal the total energy at the end. When the cannonball strikes the ground, it's going to have less potential energy because, well, it's lower, but it probably has more it probably has more kinetic energy now because it's fallen further. So when you add those two numbers up, the idea is it should be the same total as it was before. So I could even write this: the total energy after is the total energy before. And that's what we call the conservation of mechanical energy. We say that the mechanical energy is conserved. Now you have some sense of why we say that gravity is a conservative force. It might take the kinetic energy away. When you throw a baseball up into the air, it slows down on the way up. So gravity takes away the energy, but it gives it right back. It conserves it in the end. Okay, conservation of mechanical energy. And emphasis on mechanical because we're not accounting for the chemical energy locked up within the baseball. Even if that baseball was just sitting there, couldn't you extract some energy from it? Couldn't you light it on fire and watch it burn for a while and use it to heat water or do something useful? There is energy inside, but we're not concerned with that at all in this class. We're only talking about kinetic energy and potential energy in this class. Okay, one other point here before we use this equation. The only reason we could equate the two energies before and after is because we said that there was no work done by other forces. If there were somebody, if let's say the wind was blowing against the baseball as it was moving, then that would be removing some of the energy, and the energy at the end would actually be less than the energy at the beginning. So you can only argue that energy is conserved if gravity is the only force, if work done by other forces is 0. Okay, so we go back to the cannonball problem. Where's the picture? Now, this is so simple. This is probably the way you would prefer to do the problem. since the only force here is gravity, there's no other forces, we can argue that the energy at time 0 should be the energy at time 1. K0 plus U0. I'm not going to write UG0. Let's just write U0 for now. Later, we're going to have to worry about another type of potential energy, spring potential energy. So we have to distinguish between U sub G and U sub spring. But right now, there's only gravity. That's it. You just say that the total energy at the beginning has to still be there at the end. And very often, you're fortunate enough to cross out one or more of these terms. Since we're, I'll say since we're using this formula for the potential energy, and I've put my origin, if I say that y equals 0 is down here on the ground, well, when you plug in y equals 0, mg times 0, you'd find that the potential energy is 0. That was the whole point of setting it up that way, right? Anything at the origin has no potential energy under those assumptions. So we can say that the potential energy at the end is 0. So don't be confused by this subscript 0. This is not the potential energy at y equals 0. This is the potential energy at time 0. That's how I'm using the subscripts. T sub 0 is the time at which it's launched. So this would be the potential energy when it's launched. And that is not 0 because the ball is up here, not down here. Okay, so this is the one I can cross out. The y coordinate is 0 at time t1. Okay, 1/2 mv naught squared plus mg y initial. I'm just using our formula now for potential energy, mgy, equals 1/2 mv final squared. And this is the same equation that we got previously. Divide by m, multiply by 2, take the square root, and you'll find that it's, let's see here, v naught plus mg y naught. And you might be thinking, hey, that's not, oops, not mg, 2g. Oops. You might be thinking, that is not this equation, but it is, because remember the displacement? You plugged in, yeah, here we go, negative, negative, we get positive 10. I just kind of skipped that in this method. Okay, so I think you'll agree, this is probably the simplest way to set it up. Definitely simpler than solving this problem with kinematics, and arguably simpler than the way I did it the first time. So if you just take, if you're using the method where you can assign a potential energy to any mass at any y coordinate, that often greatly simplifies the setup of the problem. And I'll just say it again, even though you could rewind and watch me say it. What are the assumptions behind using this formula? Well, number one, G is constant. We're not worried about the fact that gravity gets weaker as you go far from the Earth. The mass is constant. And lastly, we also have to assume that we're setting the potential energy equal to 0 at y equals 0. So on the ground or the floor, wherever your origin is, that's where the potential energy takes on a value of 0. Let's use that same relation again in another problem. Number 14 is about a hydroelectric dam, although you'd never know that from looking at my drawing here, but here's a cliff. No, not a cliff, it's a dam. And there's some water flowing over the dam, and it descends through a height of 25 meters, which is 80 feet or so. And it falls onto some type of turbine. That's not really a subject for this class, but you might be surprised to learn, if you don't know this already, that almost every type of power plant that exists involves spinning a turbine, which is attached to, think of it this way, it's attached to a bunch of magnets, and the magnets are being made to spin inside of coils of wire. And if you can do that, if you can make magnets spin inside coils of wire, you can make electricity flow. It's as simple as that. It's like magic, but it's very explainable. Take 3B and you'll learn about how that works. And when I say spin magnets inside coils of wire, well, it turns out that even the magnets are coils of wire, because when you have electricity passing through coils of wire, they behave like magnets. So it's really just a bunch of wires spinning inside other wires. I think that's sometimes called a dynamo. Anyway, you need some way to make that turbine spin. Very often, you just boil water and make steam, and the steam makes the turbine spin. You can do that with coal, natural gas, oil, whatever, nuclear materials. In this case, we're letting water fall onto the turbine blades. And it probably doesn't look anything like this, the actual turbine. I'm sure it's a little more sophisticated, but that's the idea. So what we're really doing is using the gravitational potential energy of the water, which it gets transformed into kinetic energy, and then using that kinetic energy to generate electrical energy. There's a whole bunch of energy transformations going on. The water up here has potential energy, which gets transformed into kinetic energy by gravity, and then via the electromagnetic design of the generator, you get electrical energy out the other end. And it's useful to consider also, before we do this problem, how did the water even get up here? Why does it even have that potential energy? Did they hire a bunch of people to get buckets and scoop? Like maybe there was like a team of 1,000 people that go to the nearby lake and scoop up the water in buckets and carry it all the way to the top of the dam and then just dump it out so that the water has its gravitational energy. It seems a little inefficient. Who would want to do that job? That sounds like a lot of work. No, we let the sun do it for us. The sun is what puts all the water up there, right? How does it do that? It evaporates water, evaporates seawater, I presume, fresh water, rainwater, and the water gets vaporized and goes way up into the atmosphere where it has even more more gravitational energy, but eventually it rains back down and has less potential energy, but it's still got some potential energy compared to what it would have if it were here. And I challenge you to think of some other means of electricity generation or electrical power generation that doesn't involve the sun. Nuclear, okay, fine. Nuclear is different, but try it. Just sit there, think of all the ways you can imagine of making energy and see if you can remove the sun from that process. Because if you follow the energy trail backwards, eventually you're going to find it gets to the sun. And even for the case of nuclear power, where they split uranium, they fission uranium in order to boil the water, that may not trace back to the sun, but it does trace back to another star many billions of years ago. So I really can't think of a single means of energy production that doesn't involve a star at some point. That's not really a topic for this chapter, is it? Okay. How much water has to fall from this dam in order to generate this kind of power? 50 megawatts. That's enough to power a small town. Certainly not enough to power Los Angeles. One megawatt is like a village. So a megawatt is 1,000,000 joules per second. Every second, we need 50 million joules per second being transformed from the kinetic energy of the falling water into the electrical energy at the output. And now they tell us that this thing is only 80% efficient. So let's worry about that in a second. But we can do it this way. The power, that's the energy over time. Well, where's the energy coming from? It's the transformed potential energy of the water. So I'm just going to do this. I'll say delta U gravitational over delta T. If the water is losing X amount of joules every second of potential energy, then the idea is all of that energy is being transformed into electrical energy. Simple as that. So I don't even need to write down an equation like delta K plus delta U. If you wanted to make the problem more precise and talk about how the potential energy is first transformed into kinetic because it's falling, and then from kinetic into electrical, you could do that, but it's not necessary. Let's just jump straight to the before and after. Now here's where we need to worry about the efficiency. For every 100 joules of potential energy that the water loses, only 80 of those joules are actually converted into electrical energy. That's what they told us in the problem. The generator plant is only 80% efficient. So let's go ahead and put a 0.80. So we've already accounted for that 80% efficiency. This needs to still come out to be 50 million joules per second. All right, so 50 million joules per second needs to equal 0.8 times the number of joules of gravitational energy lost per unit time. And here's where we can use mg delta y for our change of potential energy. Now, what do they tell us about the amount of water falling? Yeah, how many kilograms must pass through the turbine each second. So let delta T equal 1 second, and then find the amount of mass. How many kilograms does M has to represent? Does M have to represent, excuse me, in order for this quantity to come out as 50 megawatts. So we're solving for M. P delta T over 0.8 divided by delta Y. All right, I'm just going to plug in numbers now. That's my 50 million joules per second. And my time interval is 1 second. The efficiency 0.8, that's dimensionless. And then delta Y, we're told, is 25 meters. Okay, are we getting the units that we intended? It's not clear, is it? Joules over second times second. Well, that would be joules. Joules over meters. Isn't a joule a Newton meter? What am I doing wrong here? I like to check units sometimes, and this is not coming out right. I would get units of newtons here. So fine, I'll pause and we'll figure out what happened. You probably saw what I did wrong. I forgot to divide by G. I dropped the factor of G. So I added a G down here. This is power times time interval divided by 0.8, divided by G, divided by Y. And now the units look like they come out correctly because seconds cancel here. Now a joule is a Newton meter. The newtons get canceled by this Newton. I've written 9.8 as newtons per kilogram instead of meters per second. And the meters in Newton meters get canceled by this meter. And we see that what comes out up top is kilograms. So let's figure this out. 50 million divided by, excuse me, 50 million divided by 0.8, divided by 9.8, divided by 25. Whoa, can that be right? That's a lot of kilograms. Well, we are talking about a 50 megawatt electrical generating station. It's going to take a lot of falling water to produce that much power. Now, if the water were falling faster, perhaps you wouldn't need as many kilograms, but that would require dropping it from a greater height. This really isn't that high, is it? So we're going to have to drop a lot of water since it's not falling all that fast. 255,000 kilograms. I'm rounding to 3 digits. So in other words, 255 metric tons. Wow, that's a lot of water. That means that this structure would have to be enormous and made out of really strong materials to support the weight of that much water. Next up is problem 1017. But before we can do this problem, we really need to basically have a little mini lecture here about Hooke's law, spring force, and spring energy. So I'm going to go straight for the more difficult setup for springs, where we imagine that the spring has been compressed rather than stretched. And it really doesn't matter either way, but here's a spring at equilibrium at the top here. Let's just suppose that this is how long the spring is naturally before it's been stretched or compressed. And then we've taken this block of mass M and used it to, well, we've attached it to the spring and squished the spring all the way down to this length here. So I'll remind you that this displacement here is called X minus X equilibrium. X refers to the, X refers to the current location of the end of the spring. So this is the X coordinate initially of the end of the spring, and it's been displaced from its equilibrium coordinate over here. So in this case, the displacement would actually be a negative number. And the final position of the spring is here. So I've labeled this distance here. This is X final minus X initial. And I put absolute value signs here just to emphasize that I'm really talking about a distance. So I should also label this. This would be x final minus x equilibrium. And this would also be a negative quantity because it's to the left of the equilibrium. Up, I goofed that. The arrow should end here. Yeah, where the end of the spring is. Okay, so the magnitude of the final stretch from equilibrium, or compression in this case, that magnitude is less than it was originally. Basically, we would compress the spring and then allowed it to expand a little bit. Now just think about it physically. What's going to happen to this block as this spring is expanding? Well, the spring pushes that way. I could call this spring force initial. This would be spring force final, Fs spring final. And I tried to draw the initial spring force to be longer than the final spring force because here the spring is compressed more. We know the more that you compress or stretch a spring, the harder it pushes or pulls. And I've already looked at that in a previous video. We call that result Hooke's law. And it says this, that the spring force is proportional to the displacement from equilibrium. So this would be positive if you've stretched it. Usually that's the way the coordinate system is set up. And this would be negative if it's compressed. Now, note here that the displacement is a negative quantity because this x coordinate minus this x coordinate would be a negative number. That's assuming to the right is positive. But the spring force is to the right. So the force has the opposite direction of the displacement. The spring has been displaced in the negative direction here, but the force is positive. That accounts for the minus sign in Hooke's law. So you really need to know that. But down here, I'm going to calculate the work done by the spring as this mass is allowed to get launched from here to here. And it's probably still being launched, but we have to pick two arbitrary locations. So first ask yourself, is this positive work or negative work? Well, the block is being pushed to the right and the spring force is to the right. Same direction, we're talking about positive work. That means delta K would be positive. That makes sense. When you look at the picture, it looks like the block is being sped up, accelerated, so that its kinetic energy is increasing. Okay, well, we know that work done is the integral of force over position. In this case, it's the spring force that we're integrating, and we're going from x initial to x final. The only way to integrate this is to know how the force depends on position. But we do know how the force depends on position. That's what Hooke's law tells us. So let me insert Hooke's law. I will pull out the negative k because that's a constant. And so I'm actually integrating x minus x equilibrium dx from x initial to x final. Now there's a number of ways you could go about this. I believe your book does basically a U-substitution. So why don't we do this? I'm going to use techniques from calculus. Because look, I could say, well, the integral of this is x squared over 2. And the integral of this, because this is just a constant, I could just call it x equilibrium times x. But I'd prefer to do it the way your book does it. So let's let u equal x minus x equilibrium. Call this the letter u. And then du, if you take differentials, this is just a constant. So we really just have to take the differential of x, that's dx. Now if x equals x initial, I'm looking at my lower limit here, that would mean that u equals x initial minus x equilibrium, right? You just plug in x initial for x, and that's how I figured out that u would take on this value. So I'm determining my limits in u here, since I'm going to rewrite the integral in terms of u. If x is equal to x final, then u would take on the value of x final minus x equilibrium. So I can go over here now and finish the integral. The work done by the spring would be negative k. So now I've got an integral with respect to u instead. And I'm just calling this u, so it's u du from the u limits I just determined were x initial minus x equilibrium to x final minus x equilibrium. These are the two limits on u. And this is easy to do because we know that the antiderivative is u squared over 2. So I get a negative k over 2 times u squared evaluated at these two limits. Okay, well, normally you do final or upper limit minus lower limit, but you've got that minus sign in here. So that would switch the order. So I could write this as 1/2 k x initial minus x equilibrium squared minus 1/2 k x final minus x equilibrium squared. Okay, so should you memorize this formula? This is the work done by a spring. I guess I should put SP for spring, SP. This is the work done by a spring in going from x initial to x final. I would say no, probably not worth memorizing. You do need to know how to write the integral, how to set up the problem using the definition of work and Hooke's law. But here's what we're going to do instead. Just like we did for gravity, instead of talking about the work done by a spring, let's instead talk about potential energy. So if I go over here to the picture again, if your spring started out like this and you put a block right here, you attach the block and squeeze the spring all the way over to here, didn't you just store potential energy in that spring? And when you allow the spring to expand again, you're releasing some of that potential energy. So the more compressed it is, the more potential energy it has. Now, would you agree that if you were holding this with your finger and then you took your finger away and allowed the spring to expand again, wouldn't you be losing potential energy? If the spring is becoming less compressed, you are losing spring, or sometimes it's called elastic potential energy. So delta U in this scenario is a negative number. There's a decrease of spring energy, but we already agreed that the spring is doing positive work on the block. The block moves to the right while the spring pushes to the right. So the work done by the spring is positive. That means that delta U and work have opposite signs, just like they do for gravity. And with similar reasoning to the reasoning I used for gravity, let's just think of it this way. What if we find that the spring did 10 joules of work here while it's expanding? How much do you think the potential energy changed by? Well, it dropped by 10 joules. So it's the same number, opposite sign. It's this old relation again. The change in spring energy has the same absolute value as the work done, but opposite sign, just like gravity. So now we can go back to the result that we found here and say that the change in potential energy for the spring is the negative of the work done by the spring. And that would be 1/2 k, and I'm going to abbreviate this as delta x final. So delta x means the displacement from equilibrium, but that's delta x final squared minus 1/2 k delta x initial squared. We'll look carefully at the beginning and end of that equation. The change in potential energy, I didn't mean to cross that out. That's supposed to be an underline. Delta means final minus initial. Final minus initial. It's staring us in the face. The formula that we should use for potential energy is 1/2 k times displacement squared, because it's a little subtle here, but the formula could include a constant, like plus c, but when you go to subtract, the c's would cancel anyway. Let's just take this to be our formula for spring energy. It's 1/2 k delta x squared, where delta x is the stretch or compression. It could be a positive number, could be a negative number. It doesn't really matter, because when you square it, the minus sign would go away. But that will be our formula for the elastic potential energy in specifically a Hooke's law spring. I say Hooke's law because real springs don't necessarily behave this way. If we say Hooke's law, we mean that if you stretch a spring twice as much, it pulls back twice as hard. If you stretch it 5 times as much, it pulls back 5 times as hard. That's an ideal so-called Hooke's law spring. If your spring really behaves that way, then this is the simple formula for the energy stored in your spring. You can either stretch it or you can compress it. 1/2 K delta x squared. And you could just say 1/2 kx squared if you want to abbreviate it. But notice that this formula kind of implies that if your spring, I almost said string, if your spring is neither stretched nor compressed, delta x would be 0 and the potential energy would come out 0. So the 0 point here is when it's not stretched or compressed. Totally intuitive. That's the easiest choice. We're using the formula so that when the spring is neither stretched nor compressed, the potential energy takes on a value of 0. That's analogous to the situation with gravity, where if your mass is on the ground, so to speak, it has 0 potential energy. Okay, let's use that now in our problem. And I think we can go ahead and introduce the next level in our energy equation before we do the problem. We're going to start from F equals ma in integrated form. Remember, this comes from F equals ma. Let's break the work up into work done by gravity, work done by springs, and then, you know what? I'm going to go straight to saying non-conservative. Both of these forces are conservative forces. When you compress a spring, like that's what this problem is actually about. If you throw a mass against a spring, the mass slows down and stops for a moment when the spring is fully compressed. So the spring has taken away the kinetic energy, but then it's going to launch the mass right back where it came from. So it will return the kinetic energy. In other words, it didn't dissipate the energy, it just transformed it from kinetic to potential and then back again. It's a conservative force. These are both conservative forces. And then the total work done would have to include, why am I doing round W's here and angular W's here? I'm inconsistent. This would be all other forces besides gravity and springs. We consider those non-conservative, like ropes that are being pulled by people. Friction would be an example. Air drag, a contact force from some other object. Those are all non-conservative forces. Set that equal to delta K. But now we use this relation. For any conservative force, the change in potential energy associated with that force is the negative of the work done. So this is the negative of delta U. This is the negative of delta U spring. And here we've got non-conservative work. Now what we do is we take all the delta U's, stick them on the other side. So work done by non-conservative forces would be delta K plus delta UG plus delta U spring. And that is a great starting point for many problems. If there is no non-conservative work being done, we'd say if non-conservative work is 0, then we have this, 0 equals, now I'm going to write final minus initial. Delta K means K final minus K initial. UG final minus UG initial. U spring final minus U spring initial. And then I do the same thing I did previously, put all the initials on the other side. So I've got K final plus U spring final plus U gravity final equals K initial plus U spring initial plus U gravity initial. All we're saying is, yes, as this spring is bouncing around, the kinetic energy might be changing. The kinetic energy at the end might be different from that at the beginning. The spring energy might be changing, same for gravity, depending on the problem. But when you add them all up, the sum is what remains constant in time. So we could just summarize this by saying total mechanical energy at the end should equal total mechanical energy at the beginning. Again, that's only true if the non-conservative work is 0. It's just accounting. All we're doing is energy accounting. There's no vectors. There's no components of vectors, simply scalars. A lot of these problems are easier to do than the problems we solved in chapters 5 through 8, I'll say. So now let's look at the problem at hand. This is going to be number 17. Okay, the statement of the problem says that a physics student places her 500-gram physics book on a table. So here's the book of mass M, and she used it to squish a spring. I guess because she's in a physics classroom, there just happens to be a spring mounted on the wall. So up here, I've tried to draw the length that the spring would have in its relaxed equilibrium state. So it's obviously been compressed from its equilibrium length. We're told that the compression is 4 centimeters. I'm using the subscript I for initial. So this is the displacement of the end of the spring. In this case, it's compression. So usually we would consider that to be negative. And we're told how stiff the spring is. Now, 1250 newtons per meter means that you would have to pull on the spring with the force of 1,250 newtons. That's what, 300 pounds, in order to get it to stretch by 1 meter. But that's a little hard to interpret because, first of all, most springs cannot actually be stretched by 1 meter. They would break. And it's also just a big number. So remember that 1 meter is 100 centimeters. So take the decimal point 2 to the left. You could also say it takes 12.5 newtons or 3 pounds just to stretch it 1 centimeter. And that's a little easier to conceptualize. You can imagine grabbing a spring, just stretching it by 1 centimeter and pulling on it with a force of 3 pounds. Okay. And then she's holding the mass here, and then she allows it to get launched by the spring. And we're supposed to figure out how fast is this thing moving after it separates from the spring, keeping in mind that this table is supposed to be frictionless. So basically, hardly anything about this problem is realistic, but this should be easy. We could start with this equation, which is always true because it comes from F equals ma. Okay, not always true. If you're talking about electrons and protons approaching the speed of light, it doesn't actually work very well, but that's neither here nor there in 3a. We could start there, or we could invoke the result that we just developed, which is actually applicable here because as far as I can tell, there are no non-conservative forces in this problem. At least none that are doing any work. It's true that there's a normal force which points that way. So as this block is being pushed to the left by the spring, there is a normal force, but it's not doing any work because I wasn't flipping you off there. That just happened to be the finger I was using. As the block moves to the left, the normal force is perpendicular. And we know that a force perpendicular to displacement doesn't do any work. So don't have to worry about that. Gravity, by the same token, gravity is not doing work. Gravity points this way. The displacement is that way. There's no mention of friction. And remember, she removes her hand when she allows the block to be launched. So she's not pushing on the block anymore either. That means the work done between the time it's released and the time it's separated from the spring, the only work done would be the work done by the spring. So we can go over here and use this equation and argue that the mechanical energy before the block is released should be the same as the mechanical energy after the block has been released. So I'll go ahead and use initial and final. Energy final should be energy initial. We've got kinetic energy we have to worry about and spring energy. We don't need to worry about gravity energy because there's no change in the y component. Kinetic energy initial plus U spring initial. Please don't forget, the only reason I can use this is because I know that there are no non-conservative forces. If there were non-conservative forces doing work like friction, somebody pushing on the block, somebody pulling on it with a rope, then these would not be equal. Okay. Can I cross anything out? Well, before the block is launched, it's not moving. It has no kinetic energy. Also, after the block has separated from the spring is no longer stretched and it's no longer compressed. Now, in real life, wouldn't the spring be bouncing around for a little bit, which means I guess it would have some energy, but we're talking about an ideal spring. We just ignore those effects. So after it's separated, the spring is neither compressed nor stretched, so it has no stored energy. And all we have to do is say that the kinetic energy of the launched block comes from the stored spring energy. This is actually a very trivial problem. After you've already done the legwork with deriving the equation and coming up with the formula for spring potential energy, once you know how to use the formulas, this is super easy. So 1/2 m v final squared is 1/2 k delta x initial squared. The 1/2s go away, and I find this. Delta x initial times root, and I guess I should really go with absolute value here, because for a compression, you might be using a negative displacement. I've got the square root of k over m. Excuse me, root k over m. Okay, I'm going to plug in those numbers. Let me do what's under the radical first. I'll take the stiffness of 1250 and divide by the mass of 0.5 kilograms, right? 500 grams equals, then I take the square root. I get 50. I multiply that by the displacement. Now I need to use SI units. 4 centimeters is 4/100ths, 0.04. And I get 2 meters per second. And notice when I plugged in K, I did not use the value that's convenient for your imagination. I used the SI value. Okay, let me confirm that same number was reached by your book. 2 meters per second, yes, okay.